Swayam Prabha. Digital India. Educated India.
Welcome. So, in the last class we have ended up discussing about the Monte Carlo simulations, and we gave an example of the bead spring model, and I already showed you the basic algorithm of a Monte Carlo simulation. So, today I will take it further and first tell you like how do we get the acceptance and rejection probability, and then I will tell you some practical tips for a Monte Carlo simulation. So, just to recall the steps of the Monte Carlo simulation, so we start from a configuration which I represent using curly bracket Ri, indicating the positions of bead. Then I do trial displacement, for a bead chosen randomly. So, the key here is that we should always choose with a uniform probability, that is like all the beads must be chosen with equal probability if, for example, we are choosing, if we are doing a large number of Monte Carlo steps. It should not be that a particular bead is chosen with lesser probability compared to others. Of course, that will be true only when we do a large number of Monte Carlo steps. And then we compute energy change due to trial, that is delta U is U of Ri prime, where Ri prime is the new position minus U of Ri. So, keep in mind that all the energies that we have discussed, like the elastic energy and the excluded volume interactions or Lennard-Jones interactions, they all depend on distances. So, as soon as any bead is moved, all these interactions are changed, and that is why we are interested in the energy change from the move. And then accept or reject the move using some function of delta U. If I accept, basically I set Ri to Ri prime, and if I reject, of course I do nothing. And then I repeat two to 4 until some sort of convergence that I will elaborate in this lecture. Okay. So, the first thing here is to determine what the condition of acceptance or rejection should be, and that is where we will use a condition that is known as detailed balance, that is very essential to the Monte Carlo simulation. So, the detailed balance essentially requires that when the system reaches equilibrium, of course, when we start with a random configuration, we do not hope that we are at equilibrium, but if I keep on running it, we do hope the system will reach equilibrium. When the system is at equilibrium, then the number of forward transitions should be equal to number of backward transitions. If something is going in that direction with some probability, the reverse should also happen with the same probability, or the number of transitions should be the same in order to be at equilibrium. So, in most Monte Carlo algorithms, we demand the detailed balance to be true. Detailed balance by itself does not give me the function p, but it tells me which functions will be workable functions, which functions I can use that satisfy the detailed balance criteria. So, the basic condition is the number of forward transitions equal to the number of backward transitions. So, let us say that we talk about two particular configurations, one of them I call O and one of them I call nu. The old and new configurations, so as to speak. Then the system at equilibrium will have certain probability to be in configuration O and certain probability to be in configuration N. We do not know essentially what that probability is, we will come to that in a moment. So, let us say NO means the probability for configuration O to occur and NN be the probability for N to occur. At equilibrium, that is very important. So, we do not start from equilibrium, but we want the detailed balance to be valid from beginning of the simulation. So, now of course, when I am doing this trial displacement, there must be a probability of going from old conformation to the new configuration. So, let us say pi O to N represents transition probability from O to N, and similarly the reverse can also happen, N to O, and we have transition probability from N to O. Okay. So, now what the detailed balance demand is the number of forward transitions and the number of backward transitions. The number of forward transition, the forward here is old to new and backward is new to old. So, the number of forward transitions depend on the number of states that correspond to the old state multiplied by the probability of going from O to N, or must be proportional to the probability of being in the old state multiplied by the probability of going from old to new. So, the forward transitions will be N O multiplied by pi of O to N. Okay. So, only those configurations which are already at O can go to N with the probability pi O to N. and then similarly only those which are at n can go to O with probability pi of n to O. So, this is my condition of detailed balance, and now we will see how does it help me to give me the acceptance or rejection criteria. So, we start with the condition that I reproduce here. And let us look at what the transition probability is equal to. So, the probability of going from O to N depends on, in our algorithm, depends on how many trials we make that are going from O to N and how many of those trials I accept. Okay. So, let us say if alpha O to N represents the number of trials from O to N, okay, or more specifically the probability of trials from O to N. We can make of course many trials, only the probability of trials that goes from O to N should be considered, multiplied by what is the probability of accepting those trials. So, while the alpha depends on how I am doing the trial, acceptance will depend on the energy condition that I employ to reject or accept a trial. So, similarly I can write for N to O so using equations 1 and 2 in the detailed balance condition star, what we do get so this sets the rule for the Monte Carlo algorithm. We can have some liberty in how I am choosing a trial move. We can have some liberty in how are we accepting or rejecting the move, but in the end whatever we do, it must satisfy this particular condition that comes from the detailed balance. Okay. So, in the one of the most common algorithm is the Metropolis algorithm that we will discuss next. So, in the Metropolis algorithm, what we do assume is I will make trials randomly in all possible directions. For the purpose of making trials, I will not differentiate between any configuration. Okay. So, if for example, I have 10 configurations possible, then I can make trials both forward and backward with equal probability, only the acceptance criteria can differ. So, in this case, I will assume alpha to be the same for both forward and backward transition, and now I am left with So, now finally, we already have discussed something about the Boltzmann distribution, the probability of the system being in the particular configuration depends on what is known as the Boltzmann factor, actually proportional to it. So, in fact, if I look at the ratio of probability of the new and the old configuration, they will be essentially a ratio of their Boltzmann weights, that is for the new one divided by the same thing for the old one. So, from here what I get is essentially exponential of minus beta delta u, where delta u is the energy change when I go from old to the new configuration. Okay. This comes from the Boltzmann distribution. Of course, there is a proportionality here, but since we look at the ratio, that particular prefactor will cancel out. So, now and beta here is 1 by kBT, kB being the Boltzmann factor and T being the absolute temperature, kB being the Boltzmann constant, sorry. This entire thing is called Boltzmann factor. By the way, again to remind you, this will only happen at equilibrium. Okay. Although we start making that particular criteria from the beginning, the detailed balance is only satisfied at equilibrium. That is the demand that we are making from the simulation, and T is the absolute temperature. Okay. So, with this now we have a rule to perform the Metropolis algorithm Monte Carlo. Of course, if I go from new to old, I will have energy change of minus delta u. Again, I can have some flexibility in terms of how exactly I am going to choose acceptance probabilities themselves, but this particular ratio must satisfy this particular relation that we have got from detailed balance condition. So, in the Metropolis case, we assume so, when delta u is higher than 0, that means we are going to a higher energy state. I will use exponential of minus beta delta u, and I will use 1 when delta u is less than 0. So, if we are going downhill in the energy, we always accept the move. If we are going uphill, we accept the probability that is given by exponential of minus beta delta u. Now, to satisfy the detailed balance that we have here, the reverse probability should simply be so, for the reverse case, delta u must be negative of what we have here. So, if the reverse transition is going to a higher energy state, then I accept it with a probability of exponential of beta delta u, and I will use it 1 when delta u is greater than 0. Now, you can see if I take a ratio for delta u greater than 0 case, I will get exponential of minus beta delta u. If I take the ratio for delta u less than 0 case, I again satisfy the detailed balance condition. Okay. So, this becomes my Metropolis algorithm, my acceptance criteria is simply P of delta u is a minimum of 1 exponential of minus delta u by kbt, okay, where delta u here is u for the new minus u for the old. All right. So, now if I go back to my Monte Carlo algorithm, we have figured out how to accept and reject the move. So, I have looked at the probability of acceptance, rejection will be just 1 minus of that, and now we are pretty much all set to do the simulations. Now, there are few practical tips here that we will now discuss. The first tip is like how exactly are we going to choose the trial displacement, particularly how exactly do we program that into question. So, let us first start with that. So, what should be the trial? So, the first condition is that I will randomly choose a bead that we can do by any kind of a random number generator. But the second thing is like what should be the how exactly we update the coordinates. Okay. So, we want to do for the chosen bead, I want R I to become R I prime. So, essentially I want something like X I to X I prime, Y I to Y I prime, Z I to Z I prime if I am working in Cartesian coordinates. And now there are many ways to do it. The trick here is we must choose displacements that goes in all possible directions, because ultimately you started with random configuration, you do not know what the ultimate equilibrium is, right. So, it is always better that we do not bias our random displacement. Our displacement should be able to explore the entire space. Okay. So, to do that, the way we will do it is we start from the old position, set some maximum displacement, and generate 3 random numbers between 0 and 1, and I will tell you why. Let us also say delta 1. Here R1, R2, R3 are random numbers between 0 to 1. So, if I look at R minus 0.5, like R1 minus 0.5, R2 minus 0.5, R3 minus 0.5, all these quantities will vary from minus 0.5 to 0.5. Okay. So, we can go to minus of x, plus of x, we can go to minus of y, plus of y, we can go to minus of z, plus of z. So, we are not biasing the displacement into any particular direction, and this helps us to reach equilibrium faster. The second one is this delta 1 delta 2, delta 3, they essentially set the maximum displacements So, if the system is anyway isotropic, we don't really bias into any particular direction. So, we set delta 1 to be equal to delta 2 is equal to delta 3, and this is 2 times the maximum possible displacement, because essentially you will go from minus 0.5 delta to plus 0.5 delta. So, now what should that delta be even if it is equal? So, now you think of like what exactly will happen in the simulation. If I for example set delta to be very high, so go back to the bead spring model and let us say if I stretch a bead, if I pull a bead to a very large distance, that will lead to large elongation in the spring, that of course will mean large energy change, and if it is a large energy change, in the case of spring it is large positive energy change. That large positive energy change, if I put into our acceptance condition, will give rise to very little acceptance probability, right. So, a large value of delta will be giving rise to little acceptance probability, because every move is resulting in a large stretching of spring, or for example separation of beads to very large distances, and those moves are typically not accepted because of the Metropolis condition of acceptance. That is one problem. If on the other hand, if I start with a very small delta, now you will see what will happen. If I just pull a bead slightly, then the spring elongation will change only slightly. That would mean that the energy change will be like very small. If energy change is very small, it is more likely the move to get accepted. So, every trial move you will do will be more likely to be accepted. Okay. That is also not quite preferred, because it will take you like a very long simulation to actually get to the equilibrium state if you are very far from it, because although you are accepting all the moves, in every move you are only moving by little. So, you are not going towards the equilibrium value fast enough. So, in this case we have large acceptance probability, and it turns out both of them are not efficient, simply because in the first case I will not accept most trials, in the second case I will accept every trial pretty much, and in both the cases I am going very slowly towards equilibrium. So, as a rule of thumb, delta should be such that acceptance probability or rate, to be more concrete, goes in the range 40% to 60%. That is just a rough number. Every Monte Carlo algorithm need not follow this, but if you are doing a Monte Carlo case and if it is taking very longer, you look at how many moves are getting accepted, and maybe the acceptance rate is very small or very high. That is one thing. The second thing is, it is always a good practice for any Monte Carlo code, you vary the delta value to figure out what is the acceptance rates of moves, that is, and you find out the delta value where it is between 40 to 60%, that is when the program will be most efficient. This is like, I would say, really a rule of thumb than being any kind of a rigorous. Okay, so this is like a very important practical tip when we are doing a Monte Carlo simulation. In the next lecture, we will discuss couple more practical tips that we must consider if I am doing a Monte Carlo simulation. Thank you.